Hi, everyone. Welcome to our second and final lecture of week 7 for Astronomy 236. Today, we're going to be talking about galactic archaeology. So, how can we figure out the way in which our galaxy was assembled? And in general, in mapping the Milky Way. So, we live inside the Milky Way, which poses advantages because we're very close by to the stars and we can study them in detail. But also, it poses some challenges because we can't just fly outside of the Milky Way and get a top view. We have to look through all of this dust and we have to figure out what's happening in these bands if we want to see what's going on the far side of our galaxy. So, this is a real challenge. The first thing that I'm going to talk about today is mapping dust. We've talked a number of times in this course how dust can mess up astronomical observations. We learned about how tricky it was to deal with for BICEP 2, and we learned how it caused the astronomers in the early 1900s to believe that the galaxy was smaller than it was when they were relying on maps using stars. So, how can we learn where the dust is and figure out how to correct it? So, one way we can do that is by looking at light emitted by the dust. Like everything else, dust has some temperature, and therefore it has some warmth and some light that it radiates through blackbody radiation. So, we can use this blackbody radiation and take images over the entire sky in the wavelengths where it should be emitting. For cold dust, this is typically in the infrared or in the radio wavelengths. And we can figure out exactly where the dust is and where it's the most warm and where there's the most of it. So this is a map from the 1990s of all of the dust across our sky. You can see that there's a lot of dust in the center along the plane of the galaxy, especially towards the center of our galaxy. But there's dust outside of that area too. You can see these beautiful swirls outside, even above us and below us in the sky. So this is a real challenge for us whenever we try to deal with observations of stuff outside of our own galaxy, because no matter where we look, we're looking for dust, and we have to correct for that. We can also map dust in a different way by looking at how much it blocks starlight. So in this case, instead of looking for light emitted by the dust, we look for light which we infer must have been blocked by the dust. If you shine a starlight through a cloud of dust, you'll have two effects. One of them is that the light will be diminished. It will be less bright after going through the dust because the dust will block some of it. The other effect is that the starlight will be redder because dust preferentially blocks blue light and lets red light through. So by combining these two effects, we can infer, based on what we think the actual light from the star should look like, what the dust is doing to it, and therefore how much dust there must be. So you know this intuitively because you've all seen, I'm sure, a sunset. At sunset, when the sun is going through more of the dust on Earth, everything appears redder and it appears less bright. If you look at the sun during the middle of the day, it'll blind you. But if you look at the sun during sunset, it will be much, much dimmer. And therefore, it'll be a lot easier for you to look at it without being blinded. And of course, it'll look much redder as a result of the dust that's being blocked. So we can use this exact process to make a very similar dust map. And as you can see, you kind of get the same thing. So you see this plane of dust going through the middle of the Milky Way. And you can see that there's this a large amount of dust towards the center of our galaxy. Now, this data set was taken from Hawaii, which means that you can't look very far into the south or you'll have to look through the Earth. So we have this hole surrounding the southern hemisphere. But aside from that, it all looks pretty similar. You can see these same little swoops and rings of dust going all around the sky. There's another advantage to looking at dust in this way as well. And that is that you get some 3D information. So consider this following case. You have two stars at different distances from the sun. One of them is behind one dust cloud, and one of them is behind two dust clouds. So even though they're right next to each other on the sky, what you'll notice in your observations is that this star looks like it has gone through less dust to get here than the light from this star. So you can infer that there must be a cloud in the foreground and then a cloud in the background, and then this star is even further in the background. So this lets you figure out where the dust is in 3 dimensions instead of just looking at the light coming from it, which only gives you a 2-dimensional map. So when you take this into account, you can make these beautiful images and map out the clouds of dust in our galaxy in 3 dimensions. So this plot is showing what it looks like if we move just a little bit around our sun and kind of see the 3D nature of all of this dust. You can see the dust that's in the foreground, and you can see the dust that's in the background because it's not moving as much. You can even make a larger trip, but the data become a little bit more challenging here. And the reason is we have very good resolution. We get very fine images when we look from Earth. But along the direction of the dust, our information is very blurry because it's hard to tell exactly where those stars are. So everything gets stretched out and blurred in that 3rd dimension. And that's why you kind of have these lines that seem to be pointing all towards the location of the sun. But these are accurate, if not perfectly, beautiful and precise representations of where the dust is. And the closer you get to the sun and the closer you come back to our own point of view, the more you can see structures and the better it looks in terms of where the dust really is. So now that we've found the dust, we can actually go back and reinterpret some of the star maps, these techniques that astronomers have been using for centuries to figure out the structure of our galaxy. So we'll recall that Herschel and Kapteyn were limited when they were making their star maps by dust. But what happens if we carefully account for it and correct for it? We can make maps that look kind of like this. So what we're looking at here is kind of a slice through our galaxy. So the plane of our galaxy runs like this. You can see that this survey has intentionally avoided looking here because there's just so much dust that it's hard to correct. And what they're really doing is they're looking to see how thick our galaxy is and whether there's any structure there. And you can see that there seem to be these contours and density. Our galaxy is relatively skinny. Only a few hundred parsecs contain most of the stars. But then there's this broad distribution of stars going far away, even way above the plane of our galaxy, although they are relatively rare. So in this case, this would be the center of the galaxy over here, and this is the location of our sun. And we're essentially looking out of the plane, out of the disk of our galaxy to see where these stars are. If you add up all of these stars and plot them as a histogram, so on the x-axis, you're showing where these stars are located, and on the y-axis, you're showing how many stars there appear to be. This is a density term, so the number of stars per volume of space, and it's in log scale. So there are e to the 10, so 2.7 to the 10 times more stars over here than there are down here per equal volume of space. So if you do this, you can find some really interesting things. And perhaps the most important thing here is that there seem to be 3 distinct populations. There's a really sharply spiked population of stars that are very common. They're more common than any of the other stars, and they're very tightly distributed close to the center of our disk plane. They don't go very far above or below our disk. Then there's a second regime where you have a slightly less abundant but slightly broader distribution of stars. So it's like a disk still, but it's thicker. And we call this the thick disk. This interior spike here is the thin disk. So we have a second component of our disk. We have a really thin one that has a lot of stars very close together, and then we have a thicker one that's a little bit more diffuse, a little bit more spread out, but lets the stars go a little bit higher so we can actually separate them out in that way. And then finally, there's this really broad distribution here that has stars kind of all throughout the region around our galaxy, even if it's not necessarily in the disk at all. We call this the halo. It's kind of a very thin, very diffuse cloud of stars that are orbiting all around our galaxy. And we can detect them and infer them from these star maps that we make now with these dust corrections. So here's a schematic of what our galaxy kind of looks like. So here's the center of our galaxy. And here's the thin disk. It has a lot of stars. Here's where our sun lies. We are a thin disk star. We're in this population of common stars that are very close to the center of the galaxy's disk. Then there's a thicker disk, which is still centered on our thin disk, but looks like a disk. It just extends a little bit more away from the center, away from the midplane of our galaxy. And then all surrounding us is this galactic halo where stars just kind of go wherever they want, orbiting the center of our galaxy. So we can also use new techniques or techniques that are old, but which we have new capabilities in, like parallax. I've already showed this video before in our distances lecture, but now thanks to this new Gaia mission, this new European spacecraft, we can find the distances to individual stars and place them on a map and start to see the structures within our own galaxy. You can see clusters of stars appearing in certain places. And you can start to see large-scale trends like the thickness of the disk from Gaia, as well as just from counting the stars. And finally, even 100 years later, Cepheid variable stars still have a major role to play. So here's an image from a paper which claims to detect a warp in our galaxy. So imagine that our galaxy is flat like a pancake, but it's not necessarily. There might be some tilt upwards on this side and some tilt downwards on this side. And that's what this team claims to have found by using Cepheids to map out large regions of our galaxies. You can see that in one side of our galaxy, there's a tilt upwards of our disk, and then it's relatively flat, and then it tilts downwards over on this other side. And here's a 3D representation kind of showing this, deformed top hat type brim. And you can even see evidence for, in the positions of stars, old events such as the disintegration of clusters of stars or even small galaxies of stars as they pass through our Milky Way. So you can see this faint line of stars here, this faint overdensity of stars, and you can see other ones throughout the sky. These are the remnants of clusters of stars that passed through or passed too close to our galaxy and were stretched out by the gravitational influence of our galaxy and ended up in these long sausage-like trains of stars. They're all still generally moving in the same direction, but they're no longer attached to each other. And the longer they go, the more spread out and diffuse they become until eventually they wind up being indistinguishable from parts of our own galaxy. And that's how you get these streams of stars. Okay, we've talked about the positions of stars, but we can also learn about our galaxy from their motions. So how do stars move around our galaxy? As you would expect, our sun orbits the center of our galaxy. In this image, it's going clockwise, and it's orbiting about the center of the galaxy over here, because this is where most of the mass of our galaxy is concentrated. If you come and look from the side, though, you can see that our sun's path is not perfectly circular and that there are these wiggles and these bobs up and down. Why is this? Well, it's actually because there's mass all around us. Our sun is a little bit above the center of our midplane. We're about 20 parsecs higher above the middle of our galaxy's disk than we are below it. Therefore, there's more mass right now from our galaxy pulling the sun downwards and causing it to move downwards towards the plane, towards the center of our Milky Way's disk. But as it does that, it picks up speed and it keeps going. So when our sun passes through the middle of our disk, it has enough speed to keep going down, and it'll essentially oscillate like this back and forth forever, going up and down as it goes around the galaxy. The more extreme your height above the galactic disk, the more often and the more extreme your oscillations are. So here's some examples of orbits for stars that are in the thick disk. So these yellow lines here, you can see that the oscillations, the up and down motion as it goes around the galaxy is even larger than it was for the sun. And if you're in the halo, you could be going around in totally different ways that don't even necessarily follow the pattern of the disk. So what this means is that essentially the further you are away from the disk of our galaxy, the faster you'll be moving when you come towards it, because you'll be falling down towards the gravity, towards the mass that's gravitationally attracting you towards the center of the disk. And by the time the star falls from way above the plane of the galaxy down to where we are near the center, it's really trucking, it's really moving fast. So what this implies is that stars that are in the halo and in the thick disk are generally moving faster right now when they approach us, when they fly by us, than stars in the thin disk. And that's what we see here. This is showing the probability of finding a star with some different velocity along the plane of the sky to us. So if we see a star that's moving really, really fast along the plane of the sky, like really fast, like 200 kilometers per second or 300 kilometers per second, we can think to ourselves that this is likely a member of the halo. And if we see one moving a little bit faster, but not quite that fast, it could be a member of the thick disk. But if it's moving relatively slowly, maybe only a few tens of kilometers per second, it's probably a normal thin disk star, just like us. And finally, you can see in these motions how our own sun seems to be moving compared to other stars nearby. So what I'm showing here is an image of all of the different stars in the nearby night sky and how fast we appear to be moving towards them. And what you'll see is that over here in this part of the sky, we seem to be moving towards most of the stars. We see them as being blue shifted to us, which means that we're moving towards them and we're going to catch up with them eventually. Over on this part of the sky, we see that we're moving away from most of those stars. So what this implies is that our velocity, our sun seems to be moving faster in that direction towards this part of the sky than typical other stars in our galaxy. So we can figure out from that how unusual our motion is and then use that to correct when we try to measure the motions of other stars with respect to the galaxy. And I wanted to add this in because this was in the news last week with the Nobel Prize of the discovery of stars orbiting very close to the center of our galaxy. This movie is showing a zoom in from the essentially an all sky view to the very nearest, the very smallest region of stars near the exact center of our own galaxy. And you can see this is an amazingly detailed image. You can see this amazing dynamic range. It really gives you an amazing context of how many stars are in our galaxy, just based on how far you can zoom this image in and keep seeing more and more stars. But eventually, we will get close enough to the center of our galaxy that we get to the data that led to the Nobel Prize. So these are observations of stars orbiting near the very center of our galaxy. Now pay attention to this star in particular. It's going around something. And it turns out that what it's going around is very small because its orbit is very close and it's very massive. So here's where it seems to be orbiting. The star makes this very close passage right around this mysterious object. If you calculate how massive this object must be to be able to slingshot that star around in such a fast orbit, and yet small enough for it to be, for it to not essentially collide, the only thing it could possibly be is a black hole. And this was what the Nobel Prize was awarded to 3 astronomers in physics for last week. 2 of them were observational astronomers. One of them was Andrea Ghez from UCLA, and the other one was Reinhard Genzel from the Max Planck Institute in Germany. And finally, they awarded the 3rd Nobel Prize to a theorist named Penrose. So this discovery of the supermassive black hole at the center of our galaxy was once again made by mapping out the stars in a very particular region and seeing how their motions tell us about what's going on and what our galaxy structure is. In addition to mapping our galaxy in terms of where stars are and where they're going, we can map it in terms of what the stars are made of. So here's a plot showing the ratio of iron to hydrogen. So how much iron there are in stars as a function of how high the stars are away from the midplane of our galaxy. So recall that most of the stars that we deal with every day, including our sun, are down here very close to zero because we're very close to the center of our disk midplane. But there are other stars that orbit in the thick disk and even out in the halo out here. And what we've found is that the stars close to where we are tend to have more iron in them than the stars far out here. Now, why would that be? Well, remember that iron is produced from stellar nucleosynthesis. So in order to have a lot of iron, these stars must have been around or must have been formed relatively late in life, late in the life of the universe, in order for them to have accumulated all of the iron from the supernova that happened from previous generations of stars. And indeed, this is what we see. The older a star is, the less iron it tends to have in its outer layers. So what this means is that the further you are from the middle of our galaxy, the older the star seems to be. And therefore, the thin disk and the thick disk and the halo are older than the thin disk. We can measure the ages of these three components of our galaxy using white dwarfs and figuring out how long it's been since those white dwarfs have formed for them to get as cool as we see them. And what we can find is that out in the halo, the white dwarfs show that the average age of a star in the halo is about 11 to 12 gigayears, or 11 to 12 billion years, just a few billion years younger than our universe itself. And by the time we get to the thin disk, the white dwarfs are considerably younger. They're only about 7 to 8 billion years old on average. And our sun, of course, is on the younger side of that. Our sun's age is about 4.5 billion years. So even for thin disk terms, we're relative newcomers. You can see this same effect here. This is a plot made using observations of red giant stars. Because it's a red giant, you can infer based on how massive that star is, whether how long it must have lived, because we know that more massive stars are not going to live as long as less massive stars. So you can turn the mass of that red giant star, which is almost at the end of its lifetime, into a measurement of its age. And what we find is that the higher away from the plane, this is the midplane of our galaxy, this is the height away from the plane, the older the stars are, and we have young stars near the plane of our galaxy and old stars far away. All right, I'm going to shift gears a little bit and talk about mapping gas in our galaxy. And we have a particularly useful trick for doing that, and that's using radio observations. So recall that when electrons move from different energy levels in atoms, they can only do this in certain predictable energy differences. This is from quantum mechanics. And when you jump from one energy level to another energy level, you get a transition and release light at that particular change in energy, and that gives a particular color to the light. It turns out that this works down in the radio as well, except that radio waves have such low energy. They're so, long wavelength and therefore low frequency and low energy that you need a lot less energy to cause a radio transition than you do to cause one of optical light. So the way that this light gets produced in energies is due to what's called the spin of the electron. It's not really like a ball spinning the way we think about it. An electron can only spin in two directions, left and right, or up and down, depending on how you prefer to say it. And it turns out that these two spins have slightly different energies when they're brought next to each other in a molecule. So here I'm showing a molecule of hydrogen, diatomic hydrogen, so two hydrogen atoms that are bonded together. This one has an electron which is spinning clockwise, and this one has an electron that's spinning clockwise. If both of them are spinning in the same direction, that has a slightly different energy level to the case where one of them is spinning in the opposite direction. Changing between these two energy states causes a spectral line in the radio. And you can get this line that looks kind of like this at 21 centimeter wavelengths, so extremely low frequencies. For comparison, 21 centimeters is about this long, about 8 inches. So these are very long wavelength, low frequency waves of light. But we can detect them because there's a lot of hydrogen in our galaxy. And this is a way for us to map where the hydrogen is. So if we look for just how much light there is at this 21 centimeter wavelength, we can make a map of all of the hydrogen in our galaxy. And this is what it looks like. You'll notice it looks very much like the dust. And it turns out that that's generally true. The hydrogen, the gas, seems to be in the same place as the dust is. Now, you may be wondering, why does this hydrogen line look so weird? Why does it have these wiggles in it? Normally, the spectral lines we look at are pretty sharp and they just look like a single peak, and that's it. And the answer is Doppler shifts. It turns out that when you look at hydrogen that's moving towards you, it will show up over here on the spectral line because it'll be at slightly different wavelengths because it's been Doppler shifted. And if you look at it moving away from you, it'll end up over here where there's a positive velocity. So this is actually a way for us to peer through our own galaxy. So think about it this way. Imagine that we're here, this is our sun, and this is the galactic center. And this is our galaxy, and there's stuff orbiting all around our galaxy. There's gas that's orbiting in our galaxy and going in all of these circles, kind of all the way around. It's just kind of this disk of gas going in circles. If we take an observation of hydrogen going this way, our beam, our line of sight passes through hydrogen moving at different radius from the center of the galaxy, and it passes through them at different angles. And what this does is it lets us figure out how different regions of hydrogen appear to be moving and appear to be in different places in the galaxy. So if we take a setup like this and we observe many different lines of sight all along our galaxy, we can build up a map of where the hydrogen appears to be and how fast it appears to be moving away from us. And it looks kind of like this. So I'm actually taking this plot from a homework assignment or a lab assignment that I did when I was in college to study the hydrogen in our own Milky Way. So on the y-axis here, I'm showing the galactic longitude, or essentially which line of sight we're looking at. Longitude in the galaxy is a lot like longitude on our planet. We just go around in a circle, and these different angles are different longitudes. And on the x-axis, I'm showing how shifted the velocity of that hydrogen appears to be. And you can see that it has these very coherent, very real patterns, and that there's this protrusion here, which we'll come back to explain later. If you do a little bit of trigonometry, you can take your measurements of the velocity of hydrogen, relate that to where this hydrogen must be if it's orbiting the galaxy in the way we think that it is, and figure out where the hydrogen that's causing this emission is physically coming from. And for this data set, if you do it, you get something that looks like this. And this protrusion here ends up looking a lot like the spiral arm of our galaxy. And in fact, this is one of the first ways that astronomers figured out that our galaxy is a spiral galaxy, by using radio observations to kind of peer through the galaxy, almost like you would for an MRI scan, and slice and put those slices together in a way that shows all of these spiral features. So here's some real data from observations in the 1950s. And you can see that there are kind of these bands of dense regions of gas all around. If you look at it like this, it's a little bit hard to tell what's going on, but just to guide the eye, this this image here has added some spiral arms to show you. And you can see that it does seem like these bright regions track the spiral arms pretty well. So in this case, here is Earth, here is the sun, and here are these spiral arms that we can see going all around us. And that's how we know roughly what our own galaxy looks like if we could look at it from the outside.